find often that just rephrasing a problem or trying to be explicit about what the problem is you're trying to solve is very, very helpful. And so when I get stuck, I usually go back and just sort of like, hey, what is the thing we're trying to solve here? What is the, maybe look at it a different way. And just sort of bump up a level, like, okay, we're getting lost in the weeds here. What's the bigger problem? So I don't have this written down to show it to you, so it's on my notepad here, but not like in anything I could easily share. The way I'm viewing this, and what you're going to present, what you can talk, your half-baked idea will fit into this scheme, presumably. We're dealing with how the cortex represents structure in the world, and I see we have a model for that in Thousand Brain Theory, but the model is short. It doesn't explain everything. We have these unique locations, and we have these features that both represent you uniquely in context, and that's great. But it doesn't deal with two major classes of problems. It doesn't deal with the fact that we have a sort of a sliding scale of objects. We have the cylinder which becomes the specific cylinder, and somehow we have to share some knowledge about the generic object with the specific object. That was one of our problems that we were dealing with. And some objects have no specific features, like an egg shape or an oval or a circle or something like that. So we were struggling with this idea of like, okay, we have a solution for very specific objects with very specific features that seems to work, but we don't have this other like scale or sliding or moving from less specific to more specific. That's one. And we also call that classes of objects. You could think the cylinder and the specific cylinder, maybe one's a class of the other, something like that. The other thing we haven't really been able to do with at all is object behaviors, and that is a big hole. And maybe we won't solve the first problem until we figure out how object behaviors work. And I think object behaviors have a similar sort of dichotomy or spread. There are sort of generic behaviors, and there are specific behaviors. So I can take a generic behavior and apply it to a new object. I can take here's a procedure I do, and I'm going to apply it to this new object, which might work the same way. So somehow we're able to take knowledge from one object and apply it to another object, which is kind of similar to perhaps taking knowledge from one object's morphology and applying it to another's. It would be nice if those solutions were the same. I don't know if they would be. So I brought out, okay, we got this general problem of representation, which we only have a partial solution, sensory motor representation. And then we defined sort of two big holes in it, these classes of objects and object behaviors. And I'll just stop there for a moment and see if anyone has any thoughts about that, because it's sort of the high scale phrasing of the problem. I don't know if I've missed anything.
Yeah, with the classes of objects, I feel like we had two ways we talked about it before. One was like you said right now, that it's like the overall category of objects and then specific instances of them, versus having like a morphological model and a feature model, and you can kind of mix and match different features onto like feature models onto the same morphology model.
Are those different? How's are they fundamentally different in your mind?
It seems like one is hierarchical, where you have the overall class and then the subcategories, and the other one is like a mix and match, where you can also you can put like the Numenta logo model onto a baseball cap and a coffee mug and a plate. Like you can mix and match them. Like it's not this hierarchical relationship, basically. That's what I'm saying.
But does it become a specific instance once you start adding unique features?
Right.
Like
I think that was our assumption all along, right? You had these unique features, and then you say, "Oh, this is the specific coffee cup," and then we lose the.
But yeah, I feel like uncertainty for me is like you can have morphology can also be quite unique, like can kind of define a unique object.
Yeah, So I guess how I thought of it so far was like somewhere in the layer 4, layer 6 connections, and maybe layer 5 as well. We're learning like a feature model, a morphology model, and a behavioral model. And then the combinations of those three can make like a specific instance ID in maybe layer 2, and maybe in layer 3 we only have like the ID of the morphology or the ID of the behavior or whatever. So like basically the models are separate in the lower layers, and then in the upper layer the combinations of which feature which models are detected define the specific instance, like, oh, this
So
is
you're
the
saying
banana that walks like a person, or
So you're saying, let me review what you just said. You said 3 types of model: a feature model, a morphology model, and a behavior model. But in a hierarchy, you're saying the lower column would only be activating one of those at that time, and then that becomes. Is that what you said?
I mean, this is just speculative, and how I was
Right.
thinking of it before was basically there would be 3 model IDs, the feature, morphology, and behavior model, maybe in layer 3. And then in layer 2, which might be the object category, no, sorry. In layer 2, which would be the object category, and then whatever is the specific object instance ID would be like a combination of those 3 models that define the specific object instance.
By the way, if I were to guess, well, I'll take it back. I don't know. I was gonna say like, oh, behavior model, where's that? And it's confusing because at one point I would say, oh, that's going to be layer 5, those layer 5A cells that was the non-intrinsically bursting ones, and the ones that connect horizontally. And because that's where behavior goes. But that would be like behavior of my body. So I'll take that back. That'd be more like a learned behavior that I'm doing, like signing my name or something like that. Whereas if we're talking about the behavior of an object, that would be in the upper layers, like layer 3, right? So I was confused by that. Yeah, I'm not sure how. It's an interesting idea that these 3. But if I say there are 3 different models, are there 3 different representations of location? That's a tricky one, right?
Yeah.
Could you get away with one representation of location? And then would it be unique? Yeah, I think they have to solve the sort of location and the feature thing at the same time.
Yeah, I think if we assume that the locations are unique to each object, then they would have to be separate location representations, but it would have to be the same space, like movement moves you through those.
Right. We
the
have this
location
idea
space in the
that
same way.
we're probably not going to have 2 different path integration mechanisms.
Yeah.
So the path integration mechanism has to work on all models of space. You know, I think these are good ideas. I'm not sure they work out yet. You know what I'm saying? It's like, oh, how do you really get this to work? You know, and maybe if you have that in your head, you can present that. You know, I'm still struggling, like, oh, which of those would be hierarchical in between columns, and which would be local to a particular column. I'll just throw in one more thing to think about. So I was thinking about what are the different ways we've talked about representing space, where we have sort of this idea that we want this sort of a generic space, and then there somehow it becomes more specific for particular. You know, it's like I have to predict the generic shape of the cylinder, but now that I know that it has a particular ridge on it someplace, I have to predict that at that location, but I don't want to have to relearn the whole model. That problem, and I thought there was 3 different ways I could think of forming multiple representations with a single path integration. That's the goal, right? That you want to have a single path integration, and yet somehow form 3 different representations or 2 different representations of space, something like that. So we just talked about that. Well, one is you could just have 2 different sets of cells. I don't believe this is right. I mentioned it recently. I said, oh, well, what if the double bouquet cells are like the generic representation of space? And the perimeter cells are specific representation space. So we have two different sets of cells, and they both be doing path integration, because path integration by definition should work on both of those. And therefore we would, we could form a generic model with the double bouquet cells. I don't think the anatomy supports that very well, and it seems a little hokey. I don't know why. I'm not a big fan of it, but it's possible. So two different sets of cells that are combined together because the double bouquet cell represents the mini columns. Therefore, they're you path integration somehow like that. The second one is we've talked a lot about is you have a single set of cells represent location, but under various contexts, it becomes more sparse. So it's not like you go to a completely different set of cells, you just become more sparse. So I could take one representation A, which is at, let's say, I don't know, 10% sparsity, and I could then form multiple unique representations from that are each 2% sparsity, but they would be a subset of the larger one. So you're basically taking a broader thing and narrowing it down by dropping out bits. So that's again using the same set of cells, but at different levels of sparsity. And then the third one, which we really haven't talked about, but I threw it into my thinking, maybe we've talked a little bit about it, is that somehow perhaps you could have the same set of cells, but use the phase of those cells to form unique representations. Like one, you could have a class of objects, and then a unique one would be, you would take a subset of the cells and put them in phase. So you're not really changing which cells are active, but you're somehow changing which cells are in phase or not. And you could represent up to some number of objects that way at the same time. So you could cycle through a more generic and a less generic or something like that. For many, many years, we had no theories about how phase would play into our theories. Not that we didn't think they were important, we just didn't know how to do anything with it. And of course, grid cells told us, and place cells told us that, phase really is important, and they play a role in encoding. And so at least we have a model to start thinking about that. So only those are the three ideas I could think of to deal with this. This is not counting what you said, Vivian, it's just throwing in one more thing to think about. Do you have two sets of cells, one set of cells for location that different sparsity levels, or one set of cells and somehow use phase to make things unique? I couldn't think of anything else. Any other methods for doing this that might work. So that's what I stopped with.
Yeah, one thought on that is because I remember we were kind of discussing some similar stuff during By the Bay, and one recent thought was just that with the two populations, like the kind of dense one and more sparse, it feels harder to do path integration over like a reasonably large set of potential objects. Like, let's assume we want to path integrate over k equals 5 top most likely objects. I feel like unless those are all kind of the same one, so like they're all the cylinder one, and then that's the one that's being sparsified or something. Like it feels easier to imagine how that would work with like phase, where they're separated in time, or like, I don't know, like if at its simplest, like with kind of two populations, like you'd only do two hypotheses in some ways.
Right. You would only have two hypotheses, unless
or like, or they would have to have like the same kind of parent or like base model. So like they would all have to be cylindrical objects, and they can kind of path integrate together, but then those we can prune down to which cylindrical object it is.
Well, I think
whereas
that
it feels
one
like with
makes
the phase, I mean, it kind of makes I just feel like compared to what we're currently doing in Monty, it's potentially more limiting. Whereas like it's easier to imagine what we're currently doing in Monty, where we explore a wider hypothesis space of, because at the start we don't have any idea really what the morphology is, and so we explore a lot of different options, and that takes a lot of time. Like again, just like, I mean, at the risk that introspection isn't correct, like I feel like if you take some mystery object, and you're trying to infer what it is, like at first, I think your ideas about it are evolving quite slowly, and so maybe that's because you're through phase or something, you're cycling through almost like in serial a bunch of different hypotheses, as opposed to in like a massively parallel way exploring all of them at the same time.
I don't know. It's like, it is serial, of course, right? But you can't, I mean, until you have enough data, you can't start eliminating hypotheses. So I don't know, what's the state before you start eliminating anything? I guess I'm struggling with that distinction between massively parallel and serial. It seems
Yeah,
like,
I guess I'm just worried because I think you opened the discussion about all this stuff by the bay with like we want to have like multiple grid cells, like codes simultaneously active, or like that was kind of how it was described in the 2019 papers, and then those like all path integrate kind of independently. But it's not obvious how you would do that.
well, no,
And so I'm kind of worried that issue still exists.
well, I think it does. In fact, I'm surprised if I said something other than this. I said we've never figured out how that path integration could work with multiple
Yeah,
hypotheses.
but it seems like
That-
a phase code is like the most straightforward way to solve that problem, I guess.
Maybe it sounds like maybe the most straightforward way because I haven't worked out the details. If we start to work out the
Okay.
details, it may not work at all. I was like, yeah, there's a new idea that could solve it. Well, maybe I don't know to think about it. Yeah, well, first of all, we never got that to work. The idea that path integration over a union of hypotheses, it just didn't seem to be possible. At least not, we didn't know the mechanism how it could be done. And I suppose that, you know, phase, even using different phases is also somewhat limiting. Because if you think about different phases, you usually have a very short period of time to cycle through phases. If you think about grid cells and so on, there's, you know, the theta phase, and you can go through maybe 8 different representations in half the theta phase or something like that. But it might work out.
Sure.
We don't know. I think, you know, the other real thing to think about is like object behaviors. You know, what is going on in representation in object behaviors? It's like, it's a little bit like, you know, a cylinder with and now its cylinder has a logo on it. It's like saying, oh, here's an object, and now I know it's in a different state, and therefore I have to make different predictions. You know, it's like, it's just, you know, the staple example, it's the same object. I don't confuse it. It's not like, oh, here's a new object that's open stapler versus closed stapler. I see them as the same. Even though the features have changed. And so how do I represent that, right? I have to sort of represent that somewhere. I thought, yeah, this is still a stapler, but also this is a state of the stapler that leads to different predictions. And therefore I have to have some different representation of location if the location is going to predict something. You know, the location might not have to change. You could imagine I have a location space, and then that's projecting to some feature like layer 6 to layer 4. But then we could also add some context, another projection to layer 4, which is saying this is the state of the object. Therefore, the state of the object is like a different feature, and you can lead to a different prediction. I mean, you could still be like the location space could be the same for stapler, open or closed, but you predict different features based on context and basically on the context of the you know, the behavioral state of the object.
I mean, you would still predict the same features just at different locations, right?
Yeah, I suppose, but I bet you there's lots of examples where that isn't the case, where you know, if I look at my cell phone screen, I'll see the state of the cell phone, but I'll have different features on the screen. So clearly, sometimes we see features moving or features in different locations, but sometimes the features change. You just see different things, you know. If you open up the stapler, now you'll see components of the stapler you couldn't see before, or maybe they change. I don't know. Anyway, the cell phone is a better example.
Yeah,
So
I think the thing that always worries me when going down the thoughts about how we do the stapler and stuff like that is just coming up with a way that we don't have to store like, you know, a million points of you know, or like a million different models to have like a continuous or like near continuous representation. And of course, the stapler is very simple. It's almost like a 1D behavior.
Yeah, I think that's where like the separate behaviors from morphology models would come in, because we could learn this like hinge behavior once in however much detail we want, and then apply it to any object that has a hinge, like the stapler or a door or whatever.
Yeah. I
But then,
like
yeah,
to
then we
remind
need
you-
to wait. Sorry.
I want to remind you, I've talked about this before, but I hope you remember it. There's this trick about neurons in our synapse model, where if you want to imagine you're learning a trajectory of something, it's moving through space, and this would apply even just to your finger moving over an object. You know, if you say, okay, I'm going to divide that into 20 different points along this trajectory, like, or 20 different points on the object, and each time I have to store a set of synapses to represent that point, it's just too much memory. And what I was able to show is that if you take an SDR and let's say like it could be the movement of the stapler, but just imagine it's your finger moving across some object, and you're going from point A to point B, that you can, as you move from point A to point B, you don't have to store individual points along the way. You can store incremental synapses along the way very efficiently. And you might think, if we think about the mechanism that how I think this works, that it might be prone for errors, but it's one of those SDR tricks where, yes, it's prone for errors, but the errors are very small compared to the potential size of the space. Therefore, you will very rarely ever get any errors. So my point is, there's a way of efficiently storing a whole set of a sequence of. It's important. It's a sequence. Anytime you have a sequence, whether you're moving your finger along the object or the stapler is opening and closed, there's a very efficient way of storing that sequence with very few synapses, and you don't have to have a lot of learning points. So I know we've talked about this in the past, and you don't have to visit every point either. You know, you could pick. Let's say you take 10 points between A and B, and the next time you pick a different 10 points, it will work, and it won't relearn, and it does the right thing. So I think there's a solution to the efficiency problem when it comes to neurons, which is interesting. In Monty, if we're doing real number of things, I don't think we had a solution for that efficiency problem. Like, we had to store all these points along the way, and then sort of interpolate between them, if I recall.
Yeah, we would have to interpolate, but we wouldn't have to store every possible point.
Yeah. Yeah, I think neurons do it nicely, very efficiently. And if you want, I could walk through that algorithm again sometime.
But wouldn't the neurons also be interpolating in some sense?
Yeah, but there's a natural overlap between all the points as you move along in a sequence. So it's like if I store 10 points between A and B, I didn't really store 10 points. In some sense, by the synapses I would learn, I'd store all the points between A and B, and it would be no distinction between, you know, the 10 points I did stop at and the ones in between. It's a continuous addition of synapses as you move through space. So there isn't like unique points. It's like you would extend the synapses on a dendrite, and now that dendrite would represent all points equally between the 2 points. And as you do this, of course, imagine I'm doing it with my finger, I'm touching an object. Well, the feature will change too. And so different columns become active. So its individual neuron only has to learn, like, during the time I'm active, my mini column is active. I don't have to learn these number of synapses, but another neuron will have a different sort of span. So it's just very efficient. It really could just add like one synapse at a time, and it seems to, I think it all works out. I did the math one time. Anyway, so I mentioned that only because I don't think we have to worry about. I don't worry about the issue of like, oh, we have to store all these points with the stapler moving and closing. Oh, I think I have a solution to that one. So it's really a matter of what would be the representation of object behavior.
Yeah, but I also feel like, yeah, it's easier when it's a 1D sequence, but I feel like as the space grows in terms of where we could be, then it becomes a lot harder.
I think it works for that too. It doesn't require this to be one-dimensional. It just requires that that you're following a trajectory, whether it's multidimensional or not. Somebody's doing something here.
Yeah, I just shared a whiteboard. Because I was just trying to think through what you were saying, and I just want to make sure I understand it correctly. So I guess if we have the computational approach or whatever we do in Monty, we would just kind of lay down a series of points. Can you see what I'm drawing?
Yeah. There's a lot of
Okay.
other stuff on my screen too. It says like all these like navigate the canvas, collaborate with others. You know, these are like clues as to what I'm supposed to do. How do I get rid of all those? The screen is cluttered with like helpful hints.
I'm not sure.
I click anywhere and they all went away. Okay.
Okay. So yeah, basically, if we're observing a line, we would just be laying down a couple of points on that line. And then let me change the color. Basically, next time if we observe like a point here, for example, we would just interpolate and
You're talking about the way Monty does it today. Right?
Yeah, that Monty does it.
Yeah. Okay.
We would just interpolate between these points, or if we would observe a point, I don't know, here, we would look at this point and maybe a little bit at this point, I don't know. But eventually it would kind of represent like a space like this around it.
Yeah.
But we would explicitly store these points. And then the way I understand it, how it would be done with neurons is that we just represent this space. We don't lay down these explicit points, but we can like recognize or deal with any point in this space.
Right. Right.
So then, yeah, then it seems like it's functionally equivalent. Like if we don't look at like taking out the fact that here we store explicit points, if we just look at the behavior of what it would return if we observe another point.
I think you're right. I think in theory, unless we, once you get into it, you might find there's some holes in it, but you're right. The basic idea is that you would end up with the same result, supposedly, right?
Yeah.
I mean, it's one of those things when you do it with SDRs and neurons, there might be some other benefits that we're not even anticipating right now. But
right.
As you've described the problem, I think they would be equivalent. I think the neurons way of doing it is some sense simpler. There's no decision as to how close is this point to a previous point, or I need to store it. There's no discreteness to these points.
Yeah.
It's just like if I think of like 15 synapses on a dendrite representing a point, well, I can just extend the number. I can just basically add new synapses along the same dendritic branch as the SDR morphs between one location and another, and it'll automatically represent the entire space. So that extended branch on the dendrite, which may now have 30 synapses or 40 synapses, something like that, and it's bigger than the integration zone, but that extended branch would represent all the points in between, and reliably so. I mean, technically there could be errors. There could be mix and match errors and false jumping, but it would unlikely happen.
Yeah. So yeah, basically functionally in the sense that they can make predictions about any point in this space, they would be equivalent, but in the sense of what they store and how efficient it is to retrieve that information, the neural representation
might be more efficient.
Yeah.
And there might be some other benefits too. I don't know. There might be some like, oh, what happens when you give it I don't know, like a novel object or one that's slightly similar, where the two would behave differently in situations where the points aren't exactly in the same line. You know what I'm saying? So
yeah,
what would I don't know. I can't say what that difference should be, but SDRs have some, have properties that are surprising. So, but on the surface, yes, they would produce the same result.
Okay.
And I felt like even though I didn't like the way we did it before, like, because like, oh, that's kind of, complex, it seemed to me. I didn't see any problem with it. So
Yeah.
as long as you guys don't mind using CPU power to do that stuff. But it could, when we talk about object behaviors, we might have similar problems. I don't know. But right, but maybe we can divorce ourselves from the issue. But anyway, I just reacted again to Neil said earlier, it'd be a lot of, I don't want to store all the points between the rotating arm of the stapler. And I said, oh, I'm not worried about that. There's ways of handling that. I don't really have a good, I don't, go ahead.
So I have a question. When we talk about object behaviors, are we also considering the temporal hierarchy of these behaviors, or do we believe that that exists? Like when I'm
maybe how would you define temporal hierarchy?
So, like when I'm pressing the stapling action, for example, that would be pressing and not pressing, and you could do the pressing on the stapler maybe for something else. That's probably not a good example, but
no, that's a great example. No, I think it's exactly the same. It's just the inverse of inference, right? In inference, you have common set of sensations or movements that are represented uniquely in context. Now we want to play back a sequence. We have a unique sequence, but in the end, it has to end up with, you have to do a series of common behaviors. If you think about language, right, I have to be able to understand the words in context. And now in context, I have to be able to say, predict what next word should be said. So that's going to be a unique representation of that word, but I have to turn it into me speaking that one sound. You know what I'm saying? So you go from a set of generic to unique in context back to generic again. So in that sense, if that's what you meant. And that's not necessarily a hierarchy. That's just like out of context, in context. But there could be a hierarchy too, right? In the sense that we have a hierarchy of object features. Like we were writing in the paper. And so I imagine that behaviors would have a similar sort of hierarchy. You're trying to do some complex behavior, and what happens as you're going along with this complex behavior, things happen, and you have to adjust, and then maybe try a different solution or something. I don't know.
Yeah, it feels like there's a hierarchy of even when you do like action policies, there's a hierarchy of these action policies. And,
right. But my general rule is that even if a hierarchy is required, you can't do everything in a hierarchy. I mean, you still have to, the individual columns have to be able to do some of this. But maybe not. I mean, that's just generally I thought about it. So, all right. So yeah, the hierarchy of behaviors. We still have to, I don't know if that makes it easier or harder to acknowledge that.
I think it, because when we do compositionality in space, we're always thinking that everything is stationary. I feel that it might be that we need to think of everything as behaviors, and stationary or space is just a sub-problem of that.
Right, it might be. It could be. I'm not saying it is, but it could be.
That example.
Well, we have some objects. But maybe counters that is the fact that we have behaviors that can be applied to different objects. I don't know.
Yeah.
And some objects don't have behaviors. I mean, the coffee cup doesn't really have any behaviors. It doesn't.
Yeah. I would say that's so that this is a sub problem.
It could be a subset, right? Well, that would be a nice solution is if all behave in this way. I think it's right up there, equal to object morphology or class of objects. I know my notes here, right? They're really basic two problems that may be the same, right? And that's what you're suggesting. Yeah. Object behaviors have and object classes, and this is kind of why I suggested if we really solve the object behavior problem, it'll inform us about the object classes. that maybe you're right. So it would be ideal, if you're right, Rodney, that these are really the same problem. And we've just been thinking about them as separate problems. That might be wrong.
The last time you in the brainstorming session, you presented a paper where there's a bar in front of I think a monkey or a rat, I don't remember, but it was a bar that was moving this way, and there were some neurons that are representing just this movement, and I think when the bar was not moving, there was no representation.
Right.
And
that makes sense. That makes sense. There's two places you see those cells. One is in the lower layers of the cortex, which makes a total bunch of sense about, okay, this is representing the animal's movement through space, right? And then the upper ones in layer 3. Remember, I presented that paper distinguishing between layer 2 and layer 3.
Right.
And they were showing that layer 3 cells. Now, they were saying, oh, the layer C cells are motion sensitive or directional sensitivity. You got to be really careful, and I mentioned it at the time, because those are the layer 3 cells they were looking for. There's a lot of other layer 3 cells that don't behave that way at all. So, yeah, you have to be really careful about that. But there clearly are layer 3 cells that are responding to motion, and remember, they had small receptive fields, and some of them were end-stopped, meaning that if the line got bigger, they started responding less. So that would imply that those cells are representing behaviors of the object. They're movement, local individual field. They're not global movement, where the layer 6 ones seem to be more global. So those are clearly, and the odd thing was that in that paper, that layer 3 is classically viewed as the input to the next level in the cortex, next region, and therefore, if that we just took it on face value, what we're sending to the next region of the cortex is not an object ID, purely an object ID, but it's a motion-related object ID. But it's also, if those cells don't respond without motion, then it would imply that nothing's being passed to the next region of the cortex if it wasn't moving, which seems a bit difficult to accept.
Yeah, I think it has learned the object behavior. So because the training data that they're giving to the monkey is that the bar is always moving, so it's trying to attend to the movement of the.
It's not attending to it. The animal is specifically not attending to it. The animal specifically fixated on a dot in the center of the screen, and if the animal does not attend to that dot, it doesn't get any reward. So literally, the animal is saying, "Don't move your eyes. Don't move your eyes. Just pay attention to this dot. Just don't move your eyes from this dot." And off in the periphery, there's things flying around. They may be aware of it, but they're not attending to it. But these are out of context. Those movements don't relate to any objects in the real world. So it's kind of a weird experiment. That's the best I can do.
Unfortunately, Vivian and I have a meeting in 15 minutes. I was just thinking, would it be all right if I just quickly mention just because it related to the last
yeah, sure.
last meeting?
I'll be all right with that. Is that all right with you, Vivian? Your meeting.
So it was just because I thought it was really interesting, the conversation about how you represent kind of generic spaces, and like the example came up of like the song and stuff like that. And then we were talking about kind of like, okay, well, what is L4 representing? Like if the song is represented as a kind of spatial reference frame, and then you're moving like through that as the frequency changes, and that gives you kind of key invariance, then like what are the features coming in? And then it just kind of reminded me of the stuff we had looked at before, where we were using kind of displacements almost as features, where we talked for a while about how like maybe in certain contexts, for example, like when recognizing a face, there might be like specific displacements which are kind of more salient or more common, and that we kind of key off. And so it seemed like, I mean, it definitely doesn't solve all the problems, but like if a particular frequency displacement is and that's kind of more of a relative difference, then that's something that could maybe be stored in L4 that would kind of reignite all the songs that have in their spatial reference frames, all the songs that have that relative displacement, and then you would start kind of path integrating through those as like a hypothesis.
Displacement, I think Vivian brought up this idea, and the idea is that the input to layer 6 would have been
would be a movement. So it would be
It would
both.
be a relative movement, so it would be the
Yeah, yeah.
intervals
So
themselves.
so it would be both. So you would have the relative movement into L6, which would be like what you're sort of path integrating. But then the displacement is just a specific, could be a feature that would because basically you don't know which kind of graphs you should be even moving through to begin with. And I guess the reason I thought it might work particularly well for like songs and certain reference frames is just like firstly, music is like lower dimensional. There's fewer dimensions like we can move through. So there's a more narrow space over which you kind of need to save displacements. And then I guess the other thing is I think humans are only kind of sensitive to like a semitone change in pitch or whatever. So like it kind of, we don't have that same issue we had sometimes with this like continuous space of vision where what happens if you do like a partial displacement and like fall somewhere in between, like the displacements in music are almost more discrete. But I mean, I think there's other kind of reference frames that like it wouldn't be just a music thing. Like,
But my question to you is,
yeah.
if my assumption based on that idea was that the actual melody, which is a series of displacement,
Yeah.
would logically be learned in the lower layers,
Yeah.
5 and 6 someplace, because that's independent of the actual features that are coming in. It's
Right.
And so when you said you thought you'd learn that sequence of displacements in layer 4, I was like puzzled by that because like
No, so I'm
that's
not disagreeing
not-
with that. So that would still be there. This is more like a way of kind of like, yeah, the relative movements are what's ultimately kind of going through the whole song. But maybe there's, I don't know, just certain displacements that are ones that we've actually kind of memorized in a sense. So rather than
you're
rely
saying
more on
this-
path
you're
integration,
saying-
it's like the actual frequency change is what we've kind of memorized, and that's kind of the feature
you mean
recovering
the specific.
yeah.
Well, that's like I went back to like the idea that you have this memory, exact memory of somebody, famous artist, first doing the song. You know the key they're in, even though you don't think you know it, but you've memorized it. That's the general rule. And so there must be a memory of what the actual key was, which is like where was it on the cochlea, when that occurred. Somehow that has to be stored. So my thinking like, oh, that somehow has to be in layer 4 maybe, because that's layer 4, no specific thing.
But I kind of like what Niels is getting at, if I'm understanding it right, is that in music, we don't really have path integration. The same melody isn't the same forwards and backwards. We can't just play a song backwards in our head or skip 5 notes ahead without significant like thinking about it. Or like even just like the ABC, we have to like kind of sing it in our heads to say it backwards. So it seems like kind of a different process there.
Well, I think, well, I guess it is, although it fits beautifully with the temporal algorithm, right? The temporal memory algorithm says, I'll learn the sequence, but I can't go backwards with the sequence. So unless I hear it backwards. Obviously, I could learn to say the alphabet backwards, just like I learned to say it forward. So there's no problem with that, but it doesn't come automatically. I think that's your point, right? I can't just do path integration and go backwards.
Yeah.
Yeah, and I guess
So-
it's just
so-
that the displacements bring the kind of pitch or sorry, key variance. And
Right, but I'm not sure if it's inconsistent with everything we've said so far. Like, imagine layer 6 is representing you're passing in the displacement, and now you're not really doing path integration. You're basically just learning a sequence of those things. You're just saying, oh, here's, I'm going to learn this. This is the interval now, and here's it uniquely, and here's it uniquely. So that wouldn't, in some sense, maybe here's one way of thinking about it. Path integration doesn't work with a melody because we never go backwards. We never ever. If I learn it in reverse,
well, you kind of, I mean, depends on what you mean by backwards. Like we go up and down in frequency.
Right, right. Well, no, you're
Like,
right.
and I think it's nice that that's kind of an ordered thing. So again, I'm not trying to suggest we don't have an L6 representation for the song. I guess maybe it helps if I go back to the problem. What I thought a problem was is that, okay, that's really nice that we kind of have like a more like a morphological model of the song or whatever. But let's say a note comes in. How do we know, like if we're key invariant, how do we know which of all the endless songs we know we should like start hypothesis testing
you
and start
can't,
path integrating over?
you can't. Well,
So
first of all, you have to have at least 2 nodes.
yes,
Right.
so exactly. So what I'm suggesting is those 2 notes give a displacement, and that displacement is what you've learned in L4 and you're detecting, and that's basically
Are you
getting all
saying
the
okay? Well, this gets
Okay,
back
yeah.
to the. I never could figure how L4 could learn displacements, and even
but I guess
represent them.
we said last time that maybe the inferior
But so-
calculus
Well, no,
did that or
no,
something.
but then Vivian suggested just calculate it externally. Don't calculate it in the cortex. Calculate it externally, which is convenient if lazy perhaps, but convenient. Yeah. And say, okay, that's so L6 is getting a displacement, but L4 would not be getting a displacement. Presumably, L4 has to get. There's something that's known. For example, there are first notes of some songs that are so unique that you know what song it is. It's very rare, but there are examples of that, where the specific first note orchestration or voicing is so unique that then you say, oh yes, I know that song. So you don't have to get the interval. So my point was that it seems like L4 would get like the moment-to-moment details, but layer 6 under this theory would only get the displacements.
I think I didn't understand your point the first time, Neil, so sorry about that. I hope I get it now, because if I do, I think I really like the idea. So are you saying that the displacement could actually go to layer 4, and there we learn like a displacement model? So the displacements are essentially the features over time. So I guess we wouldn't even need layer 6. We would just learn like basically like the temporal memory algorithm. We learn a sequence of displacements.
Kind of, but I personally, I still like that we have the L6 because, like, I mean, I think you can kind of path integrate a sense in a song. Like, I can, I know Bohemian Rhapsody well enough that I can be like, okay, I want to skip ahead to like so and so bit or whatever, or like just trying to think about how that
don't you have to
how
go
this
through all the
relates
notes
to
in your
like,
head?
huh?
Don't you actually have to go through all the notes in your head?
I mean, it's long enough of a song that yeah, maybe that's why it feels like you can break it up into parts. But yeah, but just thinking about like, okay, another abstract example, like a family tree, like it feels like seeing the movement, which is like parent, like that's a displacement. So that tells you, okay, I'm on a family tree graph, and that's kind of like that's a movement you can associate with a part of that graph. But it's still useful to have the overall graph and to be able to move flexibly through it, rather than just being a one-dimensional sequence that you have to like follow from beginning to end without any deviation. But it just feels like in some spaces, like a displacement is going to be more salient than in, for example, vision, where it's like we do a million displacements with our eyes, we saccade all over the place, except for some things like faces or something. There's probably not much of a pattern to it. And yeah.
I guess, yeah, whether or not we want to have L6 or not for this problem, I like the idea that in L4 there's also a displacement model. Like instead of saying, okay, we just have like a model of relative locations in frequency space in L6, and then we have specific features in L4, which is like the person who's singing it or the instrument that's playing it or whatever. But then I can recognize it in a different instrument, because I don't think we actually said why, but I think having this just displacement model in L6 would solve that in some sense. But also I was thinking, could we have the same idea for object models, like the general morphology models, that we have like a displacement model in L6 in addition to like the feature models and stuff?
But like the problem with the I feel like 3D's general space is like you can go between any two nodes via any direction. Like there's just like a combinatorial number of displacements to deal with.
Yeah, it's a combinatorial problem, but if we just want quick detection, like we talked before about like having some displacement model somewhere just for faster object recognition, like in addition to the actual path integrated model.
Well, maybe one way, because we're going to run out of time here in a second. Maybe one way to think about this is that last week we talked about the idea that you could input a displacement into layer 6 for music. And what I hear you saying is you could also input a displacement into layer 4. In my mind, that would probably go to the mini column representation as opposed to the, being a feature. But you didn't say that, but that's what I'm thinking. So now the idea is we're just extending the idea, saying, what if displacements were passed into both layer 4 mini columns, let's say, and layer 6, and they might serve different purposes. Would that be a proper summary of that?
Yeah, I think this
think it's an interesting idea. So we just one step further from layer 6 now add layer 4. It'd be interesting to look at the literature on audition. It's always been much poorer than vision. But by now there's probably a bunch of stuff on this. It's every time in the past, past being like 10, 15 years ago and earlier, when I read about the representations in auditory cortex, it was very confusing, and I felt like the data wasn't reliable. So maybe that's changed. We might be able to find something now that seems to be better. But I like that idea. So as long as you're not throwing it away from layer 6, because I think I don't.
Yeah, I also don't want to get rid of layer 6, and I think that
do,
was a nice idea that there's like morphology.
I had a similar odd observation before we leave here. I'm thinking like, if we do path integration in physical space, you always, if you end up back at the same point, like you can return to the same point and then it's the same place. But in music, it's not the case. I could traverse through a series of intervals and come back to the same interval, but it won't be the same place in the song. It just doesn't.
But it's kind of like, because you can sing to the, like once you get given the key to the song, you can sing the right note, even though it's a new key that you may have never heard it or sung it in, right?
Right.
And that's kind of path integrating through like the frequency domain to be like, okay, this is how I should be singing A, or whatever.
Maybe, but perhaps, but in physical space, if I come back to the same location, I expect to see the same physical things. I have the same representational location, but in the music, it's not. If I come back to if the song starts on a 5th and I come back to a 5th, or I go up and down, I have to think through it, but it's just like you never end up at the same spot again. You're moving through time and you never return, it's like you never come back to the same point where you say, oh yeah. You can do that in like little sections of songs where you repeat them over and over again. So I don't know. Anyway, it's okay. Well, maybe since you have to leave and it's 11 o'clock, that was a good idea to leave on. We can digest, to think about displacements.
Yeah, and for what it's worth, like after last week's meeting when we were talking about the music stuff, I thought it could be kind of an interesting, one possibility is a first like abstract space to try and concretely solve, or I know it's not abstract, but sorry, rather like not 3D, as a way of kind of showing that what we're doing in Monty can generalize to other types of spaces, if we can figure it out.
Yeah.
But
right.
Yeah.
And in audition, you've got this weird thing. It's very critically tied to time, and we know grid cells represent 1D space very well, but unlike a melody, if you come around to the same point again, it's represented the same. In a melody, you can never come back to the beginning, unless it's a repeated little riff that goes over and over and over and over again, which we can also learn. All right, well, a lot of things to think about there. All right, well, maybe we'll have some more thoughts. No, Wednesday, we're not going to talk about this. So maybe the next time we talk about this again would be Monday then.